melted lumps. Now, to get rock to melt, we definitely need to increase the temperature. We need to decrease the pressure. And it helps if we can add in water in the form of steam, especially because the temperature is going up. It's going to be steam. And gases like carbon dioxide. Those volatiles are substances that go from a liquid to a gas very easily. And water is one of those. So if we can add those volatiles like water, it will break the chemical bonds that are holding the atoms together, allow them to move more freely, and that will transition that solid to a liquid. And composition, what minerals and materials are present in that original rock will play a big part in determining the temperature you'll need to get that stuff to melt. Because different minerals form at different temperatures, and they melt at different temperatures. So some rocks, since rocks are not created equally, some rocks are going to melt at low temperatures, some will melt at high temperatures, some will melt at medium temperatures. The mineral composition will determine that. That's kind of where we left off. Are there any questions before we get started today? Let's go wait for the rest of this definition. Yes?
What's this homework do?
Homework 2. It's on the syllabus, it's on the schedule. I have 3 classes that I don't remember all.
17th.
Is it 17th? Thank you. You know, I've only been up like an hour, so maybe I get it. It'll be morning. So that's the molten rock part of that definition. So if we're going to increase temperature, that molten rock is going to be hot. It's like melted butter. It's like the apple filling in McDonald's apple pie. Caution, constantly hot. We have to cool that. Now, the word cooling in this definition does not mean room temperature. Does not mean touchable. That igneous rock can be completely solid and still be well over 1,000 degrees Fahrenheit. It's kind of like baking a cake. You put the batter in the oven, and when the batter cooks, the cake is solid. But are you getting that pan out of the 350 oven without a hot holder? Not unless you want to go to the hospital with 3rd-degree burns on your hand. It's solid, but it's still hot. It's the same with igneous rocks. The word cooling in the definition means we're going to start with something hot, and we're going to let that temperature drop. As the temperature decreases, minerals are going to start to form. Elements will start finding each other, bonding together, and we'll get solid crystals forming. But that rock can be completely solid and still be very hot when it's done. That brings us to our next word, eventual solidification. Fication, F-I-C-A-T-I-O-N, and that's on the end of the word. That always means to make something. That's coming from Latin. You know that dead language, Latin, that did everything. Ficare is in Latin, it's a verb, it means to make. So, to make what? A solid. We're taking what was this gooey, hot material and we're firming it up. And that process is going to be from the crystallization of minerals. Any questions? All right. So, where are we going to find this molten rock? Well, there are 2 places where we can find it. It's going to be forming where we have increased temperature, decreased pressure, and volatiles, which usually, about 98% of the time, it's going to be underground. So at that depth. Now, that molten rock that forms underground can periodically come all the way to the surface and spill out onto the surface. We call that volcanism. So we can find molten rock in 2 places, underground or on the surface. If it is underground, it's called magma. Magma is molten rock that has not yet seen the light of day underground. If it's spilling out of a hole coming out of a volcano, flowing over the landscape, bubbling out into the ocean, then it's called lava. That's the only difference between those two words, is their location. Now, the igneous rocks form from molten rock. So, what two places are we going to find the igneous rocks forming? A little too specific. You're on the right track. We're going to find them forming where? Underground and above ground. Igneous rocks are going to form underground from magma we call intrusive or plutonic. That's coming from Pluto. That's what, that's Greek, I believe. Greek god of the underworld. He was the blacksmith before he ran the forge. So that's where we're using the word plutonic, the molten rock underground. That's internal, intrusive. That igneous rock forms on or at the surface from a lava, that's going to be extrusive, that's external to the earth. It's on the outside. We call that also volcanic. Roman god Vulcan, god of fire. Now, when we look at an igneous rock, which you'll do in lab in a few weeks yet, when you look at an igneous rock, you can tell if it formed underground or if it formed on the surface. Okay. Who here has experience with Legos? I think it's toys, two blocks, whatever. Duplos, not the same Lego. So yeah, you build things, blocks and stuff, okay. Who here has some experience with, hey, I bought a new bookcase, I bought a new desk, you want to go to the house and help me take it out of the box and put it together? You know, you don't want to end up with missing parts and another shelf, what do we do wrong? You know, well, this should take 45 minutes. So 2 days later, it's still in pieces. Now, if you are an element, and you're going to join up with another element to form a mineral, your atoms have to find the atoms of the other element in that molten rock. And you have to be at the right temperature so that you can form a chemical bond with each other and become a solid mineral crystal. That takes time to do that. If the temperature changes, then the temperature won't be right for you to do that, and you're going to have to find a different element to make a mineral with instead. Now, if I give you a big box of Legos, and I say, okay, here are the instructions on how to build the Eiffel Tower with these Legos. Cool. Okay. Because you open your box, and I'll say, okay, go ahead and get started. Okay, well, where's the base? Here's the base, and here's that's the top part. And then I say, stop. How many of you are going to be done? Nobody. Why? Why wouldn't you be done making the Eiffel Tower in 5 seconds? You didn't have enough time. You ran out of time. Now, if I said, here's the spots of Legos, take it home over the weekend, and build this Eiffel Tower model and bring it back, you'd have it done. You wouldn't have any of your other homework done, but you spend all weekend playing with that thing, right? You have more time. It's the same thing with elements and atoms. They need time to build those crystals. The bigger the crystals are, the more time was needed to put them together. Does that make sense? What's going to control the growth of crystals is the temperature. If the material, that molten rock, cools off too fast, there's no time for those crystals to form. You'll get very, very tiny, tiny crystals, if any. If it cools down very, very slowly, over the course of literally millions of years, you can get very huge crystals. Sometimes individual crystals the length of a row of tables in this room, or bigger. Where are my fudge makers here? Fudge makers? Fudge eaters? You've seen fudge being made? All right. So you're making the fudge, you got your sugar melted, right? And you're boiling and bubbling, and it's so good and all. And then it's starting. You got the spoon. You got to put a drop. If you don't have a canning thermometer, you got to old school it. And you're putting the drops of fudge in the water, and liquid little softball. It tells you, okay, that temperature, stop. And then what do you have to do? That's got to come off the heat, and you have to stir. And you have to stir. Phone rings. Forget it. I'm making fudge. Don't have to work. They can wait and come back later. Dog needs to go outside to pee. Use the carpet on making fudge. You can't stop. You have to keep stirring until you get that nice little glossy sheen on the fudge that tells you, okay, you're done. You put it in the pan. Because if you stop and answer that phone or answer that door, that fudge is going to cool too slowly. And you'll get real sparkly fudge that'll be crunchy and gross. We've all had that fudge. We've all had that fudge. What happens is that if it cools too slowly, the sugar's got time to reform big crystals of sugar. You don't want that in the fudge. You want little tiny microscopic crystals of sugar that just melt in your mouth. Okay. You don't want to be at a party and go, oh, I have a piece of fudge. And you bite into it, it's like crunchy. Like, oh, it's delicious.
Yeah.
You stir. You're trying to get it to cool quickly so that sugar makes like tiny crystals. It runs out of time. It's the same with molten rock. The faster that molten rock cools down, the tinier the crystals will be. The atoms run out of time to find each other to build stuff. The slower, the bigger. So when you're looking at an igneous rock, that igneous rock has big, chunky, sparkly crystals in it. You know, it had to have formed underground slowly. Now, why would magma underground cool off more slowly than at the surface? Okay, you go into your kitchen, you turn on the stove top, turn on a burner, and you turn on the oven. You let them both run for an hour, and then you come in and you turn both off. Which one's going to cool off first?
One on the stove.
The top, stove top, right? Why?
Air.
It's only the air. The oven's going to be nice and toasty hours afterwards. Why? It's meant to be, right? It's insulated. Keep the heat in. The earth keeps the heat in. Rocks tend to insulate. They don't transfer heat very well. The rocks insulate. They hold the heat in longer. So that molten rock underground, that magma is going to take a lot longer to cool off. In some cases, it's been measured that some igneous rock may have taken as much as 30 or 40 million years to go from that molten state to completely solid. But on the surface, once that material comes into contact with the atmosphere or with ocean water, that's it. The temperature's going to plummet. It cools off very fast. Even some of the lava flows in Hawaii they're cool enough to walk on within a day or two. And they can be starting at a temperature well over 1,000 degrees Fahrenheit. So when we look at the rock, the size of those crystals will tell us whether that rock formed from lava or magma. So the rate of cooling, how fast that temperature drops, excuse me, choke myself up. How fast that temperature drops controls the appearance of the resulting rock. And in geology, the appearance, the crystal size, the way it looks, we call that texture. So the cooling rate directly controls how that rock will look, controls the texture. I don't realize how big this one is. Oh, I'm sorry to do it. Are there any questions? So the texture, the crystal size of the igneous rock will tell us where that rock formed, whether it was underground or on the surface. So now, if you're going to put something in the oven, say you're at a party and, oh my gosh, you have this awesome casserole thing, whatever, and you just have to have a recipe. So you get the recipe, and you go home, and then you're making it, and you look at the recipe, it says, bake for 45 minutes. Okay? What critical bit of information is missing? The temperature. Where are my bakers? A few bakers, okay. You're not putting brownies in a 350 or 325 oven for 12 minutes. That's the chocolate chip cookies. Brownies aren't going to be done. They're going to be okay. But you're not putting chocolate chip cookies in a 425 oven for 45 minutes. They're going to be crisp. Look that way. They're different compositions. So that's not going to work. So knowing how long it took for that rock to form isn't enough. We also need to know what temperature did it form at. Did it form at low temperature, medium temperature, high temperature? What's going to tell us that? The composition. An experienced baker, just trial and error, just from experience over time, will get a feel for, okay, well, it's a 15-pound turkey, it's going to be 15 minutes per pound, it's going to be, we need 3 hours for that thing, 375. You know that depending on, like my mom, she was a master, it's like, I can't quite figure this out yet, but it's like, okay, I'm going to have a roast and potatoes and a casserole, vegetable casserole, and rolls, and this and that, and there'll be 9 things in the oven. And it's like she would know, roast is first, potatoes are next, this comes out, this goes in, that goes in, this comes out, this goes in, that goes out. And she cooked like 9 things at the same time, and they'd all be done at the same time. I think so. I'm still working on figuring that out. But it's because, over time, she learned how long it takes each thing and what temperature each thing needed to be done. Because each thing's a different composition. It's the same with igneous rocks. The mineral composition determines the temperature. Different elements combine only in specific ranges of temperature. If that temperature never occurs, that mineral is not forming. Bowen, there we go, page 164. 164, you may know of it, look at it later if you don't have your free here of the book. Bowen's reaction series, page 164. Now, I'll put it on the board in a minute or two. 164. What the heck is this thing? Now, you see, Bowen was once a lowly student, like you guys and like me. Back in the 1920s, he was working on his PhD. And a PhD, any kind of degree like that, it may sound intimidating at first, and you have to do this really big research paper. It's like doing a project on a science fair, just at a higher level. So you have to come up with, what am I going to do this on, what am I going to do it on, what am I going to do it on. Well, he got an idea and probably it was one of his faculty members that said, hey, I don't know how to do this, you figure it out, kind of thing. And he had this idea that he was going to try to figure out how you get different types of molten rock. So what he did, he had a little blast furnace, he had a little oven that was capable of getting hot enough to melt things in the lab. And he got samples of rocks and samples of minerals, and he ran them through the furnace and kept records of what temperatures they formed and what temperatures they melted. And he was able to determine why there are different types of molten rock. And it has to do with the composition of the rock that gets melted and the temperature. And he put all of his info and his research in a big paper and presented and all that. And one of the ways he summarized his data was in this chart thing that's on page 164. Now, basically, in this chart, he's got high temperature at the top. And the temperature drops as you go to the bottom. And high temperatures, you're looking at about somewhere in the range of about 2,500 degrees Fahrenheit. Low temperatures are down to about 500, 600 degrees Fahrenheit or so, just as a ballpark-ish. And he has discontinuous series here. Because you notice something weird about that. And then there's continuous over here. And then at the bottom, it's just whatever's left over. Now what he noticed was that when you start with molten rock, and you let it cool down, certain minerals start to form at specific temperatures. Now, the minerals he was looking at were silicate minerals, because they're everywhere, they're the most common, and they're the most common minerals that you'll find in igneous rock. So he came up with this chart to compile all of this data, and it shows the sequence, the order, the series in which these silicate minerals form as the temperature goes down. Olivine, Roxine, Bowen. Now, this is a discontinuous sequence because what he discovered was that these minerals all pretty much contain the same combination of elements. They're all very rich in iron and magnesium. Remember, iron is Fe. Magnesium is Mg. And he called these iron and magnesium-rich silicates, he called them ferro, that's the iron, magnesium silicates. Because they are rich in iron and magnesium. Because they contain these heavy metals, they tend to be heavy. They have a high density. And they're dark in color, black in shades of green and dark green. And they are very temperature specific. Olivine forms at high temperature, down to about maybe 23, 2200 degrees Fahrenheit. If it gets much colder than that, olivine stops forming. It's just not hot enough anymore. And at a lower temperature, pyroxene will start using up the iron and magnesium instead. Pyroxene will form down to about 1800 degrees Fahrenheit, then it stops. Because if it gets below that, then it's too cold for pyroxene. Then amphibole will form instead. When that temperature drops some more, it gets too cold for amphibole, biotite starts forming. So it's a discontinuous process, very temperature dependent. It's a start, stop, start, stop, start, stop, start, stop. In other silicates, he found it's a much more gentle process, a much more continuous process. That's the word, clad of clay. At the high temperatures, at the same time that olivine and pyroxene are forming, calcium-rich, that's what Ca means, calcium-rich plasmoclated feldspar will form. This could be up to 100% calcium. As temperature drops, that feldspar continues to form at lower temperatures, but calcium doesn't like low temperatures, but sodium does. And as you go along, you start running out of calcium. So as temperature drops, you'll start getting less and less calcium and more sodium. That's what the Na is. So you'll come down here to 75% calcium, 25% sodium, then you'll have a 50-50, and then you'll have a 25% calcium, 75% sodium, and then you have 100% sodium at medium temperatures, which is your sodium-rich feldspar. And that's going to be roughly 100% sodium. There are about 12 different feldspars. You got an 80-20, you got 60-40, you got 40-60, and they form continuously. Sometimes under a microscope you can look at an individual feldspar crystal, and you can see different layers in the crystal, with calcium rich in the center, and then not so much, and then not so much, and then 50-50, and then more sodium, and then sodium rich on the outside. That reflects that drop, that gradual, continuous and gradual drop in temperature. These minerals, sodium, calcium, silicon, oxygen, no iron, no magnesium. These are non-ferromagnesium silicates. I always have this thing, it's far away from me. Non-ferromagnesium silicates. By contrast, because they do not have high iron and magnesium contents, they'll be lighter in color and lighter in weight. They have much lower densities. And finally, at low temperatures, ranging from about 500-600 degrees Fahrenheit up to about 1,000, maybe 1,100 degrees Fahrenheit, we have what are known as the residuals. These are like minerals that were formed from very low temperatures, from whatever liquid is still left in the melt. And these are the minerals muscovite mica, potassium feldspar, quartz. And these also are non-ferromagnesium silicates. Any questions? So far, so good? And there's a much better picture here on page 164. Now, he came up with this just to kind of have a figure in his research paper, so he could graduate, right? Okay. And this thing came out, and his stuff, people read his stuff, and he's on something. And then he had to present it in all these ways and blah, blah. Eventually, scientists, other scientists and his colleagues started realizing that this little chart of his is pretty doggone handy. It helps summarize not only the formation of these silicate minerals, but the formation of these minerals as they pertain to igneous rocks, igneous rock formation, igneous rock composition, cooling. It also relates back to metamorphic rocks, and it relates back to the breakdown of rocks in the sediment. This thing is like applicable to 9 different things. So that's why he's like famous now for having developed this, and it's called his reaction series. He's like world famous for it, like imperfect smoothie. So you never know when something you have to do for a stupid report to make it famous. So in breaking this down, we can look at these minerals and use them to break this down into temperature zones. Very high temperature at the top. And high. Medium somewhere in here. Again, this is on this chart. Very high temperature. If you find an igneous rock that's mostly olivine and or with calcium feldspar, that's telling you it's formed at high temperature. If that whole rock was 2,300 degrees Fahrenheit and stayed that temperature long enough for the whole rock to form nothing but olivine and calcium feldspar. If you find a rock that's mostly made of quartz and pink calcium feldspar and silvery white flakes of muscovite, that's telling you that rock formed at low temperature. Most likely at temperatures of 1,200 degrees or less. Very high temperature, we're going to have a greater concentration of the ferromagnets. These high temperature rocks will be dark in color and very high density. We're going to call them ultramafic. Maf is for magnesium, fic is for the iron. Mafic. So not only are they ferromags with a lot of iron and magnesium, they're ultra mag. So they're like 80%, 90% iron and magnesium. Really up there. Slightly lower temperatures, you're going to have mostly pyroxene, some lower calcium feldspars, maybe a little olivine might sneak in there at the top. But mostly pyroxene. That's going to be high temperature. So you're down in the range of about maybe, 2,000 degrees or so. There's still going to be a concentration of ferromagnesium. So it's still very iron and magnesium rich. These are mafic. Low temperature, you're going to have mostly calcium feldspars, maybe a little sodium feldspar, and both piles of quartz. These are non-ferromagnesiums. They're lower density. They are mostly feldspar and non-ferromagnesium silicates. Those are called felsic. I'm going to do silicon oxygen rich. They're all silicates, but the felsic has a higher proportion of silicon than oxygen. The mafic and the ultramafic are mostly iron and magnesium.
What temperature is that at?
Low temperature, typically about 1,100 or so. down to about maybe 500 degrees Fahrenheit. And then there's, no, I didn't forget it, the medium. Now, medium, in geology, we refer to those medium temperature igneous rocks. They're going to be mostly amphibole, lots of biocides, and sodium feldspar. The medium temperature, they're classified as intermediate, because they're, in the middle, they're medium. So they're going to be just about 50-50. They'll be about 50% iron magnesium rich and about 50% silicon oxygen because they're in the middle. They're kind of like half mafic and half felsic. They're not as hot as mafic, so they don't have that as much iron magnesium, but they're not as cold as felsic, so they don't have as much silicon and oxygen. This gives us the four basic types of molten rock: ultramafic, mafic, intermediate, and felsic. That's what Bowen came up with. It was like, wow, this is so cool. I graduate now, yes, here's your diploma, get the hell out of here. And then he became famous for doing this. It's like awesome. It's like, so, really? So we have now these four types of molten rock. What two places can molten rock be found? Underground and above ground. So we can find these types of molten rock in both places. That's going to give us igneous rock groups or igneous rock families. An igneous rock family is a group of igneous rocks that form from the same type of molten rock. At low temperature, we're going to get igneous rocks that are got a lot of quartz and potassium feldspar, muscovite, low temperature minerals. Intrusively, this is going to form rocks like granite. Extrusively, it'll form rocks called rhyolite, pumice, tuff, obsidian. This is the granite rhyolite family. Granite rhyolite. Which one of those two will have big sparkly crystals that make beautiful countertops? The intrusive, the granite. You're not going to see crystals in a pumice. You're not going to see crystals in a rhyolite. because if it's formed on the surface, it formed at the same temperature as the granite, but it formed much, much faster. So another time for the crystal formation. Medium temperature, intermediate, underground we get diorite. On the surface, we get andesite. Intermediate molten rock gives us the igneous rock family, diorite, andesite. Diorite's the intrusive, andesite's the extrusive. They have different textures. Diorite, big crystals, the andesite, tiny crystals, because of how fast they form. But they form at the same temperature. They have the same minerals. High temperature will give the gabbro, the salt family. Gabbro is the intrusive, the salt is the extrusive. They form at the same temperature. They're both mafic. Gabbro forms deep in the earth, the salt forms volcanically at the surface. They both contain the same minerals. They have to, they form at the same temperature. At very high temperature, intrusive will give peridotite. And extrusive, we get something called komatiite. Now, komatiite does not form today. It's a very rare rock, and it was only able to form at the surface way, way back in the Earth's early history, when the surface was so very, very, very hot. It's just not that hot up here anymore to support the temperatures you need for that rock to form at the surface. But where do we have these very high temperatures and a lot of iron deeper in the earth? That's why the mantle is made mostly of peridotite. High temperature, iron rich. Gabbro, the salt, is one step down from that. It's mafic. This makes up the rock of the ocean crust. Ocean crust is formed from the melting of the upper mantle at your seafloor spreading. As the plates separate, pressure drops, the upper mantle melts, and voila, you get gabbro and salt. Granite and rhyolite, that's what you get the continental crust formed from. Granite and rhyolite, low temperature, silicon and oxygen rich, low density, light, fluffy, buoyant. When you have subduction, when oceanic crust goes back into the mantle, it melts. The melted stuff comes back up, melts its way through the continent, form volcanoes at the surface. You're melting oceanic mafic, and then you're melting continental felsic. What are you going to get by the time it comes off the top? Half and half. Like mixing chocolate with peanut butter, whatever you get in the middle. This Bowen's reaction series will relate back to volcanism. Why volcanoes do what they do. Why some volcanoes are more dangerous than others. It goes back to mountain building. It goes back, I said, it goes back to metamorphism. It's used for like everything now. It's just a great way to organize the relationships between igneous rocks, metamorphic rocks, weathering processes. It's just awesome. I will be coming back to it periodically. Any questions?
Did you guys get an A?
That I don't know. I don't know if it got an A or not. I would hope so.
You would think so, right?
You would hope so. If not, I think, once he became Professor Emeritus, I'd be like, I want my A. I'm right there wrong. Yeah, really. Everybody uses my data now to have my A, including you to have my A. Yeah. There's always one. There's always, there's always frames. 6.0. Yeah, any questions? Now, I know there's a lot of things on this board right now, and your head may be spinning. But when you think about it, you got to remember nature likes balance. So if you have a high, you'll have a low. You have top, you have a bottom. The left, you have a right. So, yeah, exactly. A yin and a yang. So you really only need to remember like one thing. Okay. Remember, pick one. Remember either mafic or remember felsic. Because if you remember mafic, you know it's iron and magnesium rich, high temperature. Okay. You know there's got to be one that's opposite. That was high temperature, iron, magnesium rich. There's got to be one that's low temperature. Silicon oxygen rich. It's got to be backwards. It's got to be opposite. That's your felsic. Then there's one that's half and half. You should be able to remember intermediate. It's the one in the middle. Intermediate is half and half. And then ultramafic is supermafic. It's the one up from that. So it's really, it's not as bad as it looks. This instructor has been studying this for longer than many of you have been alive. No, I did not know Bowen personally. Oh, just a joking. How long have you been here? A long time. Longer than many of you have been alive. Oh, God, I wish. Any questions? Well, we're going to take a look first at some intrusive igneous rocks, some Plutonism. We got 15 minutes. I'll be gentle. It's going to be an 8-block compared to what's already up there. Plutonism refers to intrusive igneous activity. What's going on underground with magma, with molten rock underground? Now, most molten rock, some 85-90% of all molten rock, never reaches the surface. Never. It's a long way up. And on the way up, it's losing heat. It's like going to McDonald's and getting like a fresh, large fry, right from the basket. It just came up out of the oil. There's nothing like fresh fries. Drives me nuts. My sister, whenever we go somewhere, she says, "I want the fries to be fresh." Just let her go in the kitchen and bob for them in the grease. She'll be happy. It's hot, really hot. You know what I mean? You get the nights and you can smell it in the car, and you're like, book it home because you want it to still be hot when you get home, and they're cooling, and so you're trying to run the heater, and pick up the AC when it's hot. They're losing that temperature the farther away they go. It's the same thing with molten rock. That's a long way up from the mantle and the lower parts of the lithosphere and the lower parts of the crust. That could easily be 5, 10, 15, 30, 40, 50 miles that material has to travel before it reaches the surface. It's cooling and hardening on its way up. So most magma on its way up is going to almost everything. But it's going to all solidify before it gets here. Very little of that material actually is able to get to the surface to produce volcanism. So most of our igneous activity will be underground. Now, igneous rock that forms underground is called a pluton. Pluton is a mass of intrusive igneous rock. Doesn't matter what size, doesn't matter what shape, doesn't matter what depth. It's called pluton. Now, do we scientists distinguish between different sizes, different shapes? Oh, heck yes, we name everything. So there are several different types of plutons. Oh, easily, at least a dozen that I can think of off the top of my head. No, I'm not going to need to remember a dozen names for plutons. And they're called intrusions. So here's our surface. Here's what else here. Trees. Isn't that special? So we're looking at a side view. So you have our rock layers. These are our rock layers. Going down into the earth. And coming up from below, we have rising magma. Now, as that magma rises, it's hot. It can be hot enough to melt the surrounding rock as it comes up. The surrounding rock is a contradiction in terms, but it's called the country rock, meaning the rock of the country, the native rock, the rock that was already there. And then this hot stuff just showed up from nowhere. So as that molten rock rises, it's hot. And it will be just exploiting any path it can find to the surface. A fracture, a joint, a crack, a crevice, a fault, any path through the rock that it can find, that's where it's going to go. And as it's going, that heat's going out to the surrounding country rock and can be melting some of that country rock into it. That's why it's called an intrusion. It's intruding. It's butting in on the rocks that are already there. We call this process assimilation. It will be assimilated. Yeah, we got some Star Trek people here to board. Yes, question? It depends on what pathways are available to it. For example, if there are fractures or joints or cracks through the rock, it's going to make that get up there much easier. If there's already a volcano there, or there's already a tube that comes to the surface, that will make getting up there very, very quick. It's a pre-made path. But it can take anywhere from several centuries to several millions of years. Okay, does that answer your question?
Does it form anywhere, or is it just certain places?
Okay, what form? The molten rock itself?
Right.
It'll form at specific places, and that's something I'll get to a little more deeply when we look at volcanism. It's got to form in places where we can meet one or more of those three conditions, either higher temperature, lower pressure, or volatile. And those locations are going to be closely related to plate tectonics, plate boundaries. So, unfortunately, we're not going to get a lot of molten rock here in Ohio. We're nowhere near a plate boundary. At least now we're not.
I don't want a volcano next to my house.
Well, a little one, like at Maine and 3rd, would be great for tourism and skiing and stuff like that. Be a field trip. It might. I don't know. I'm going to do that big traffic circle and just go around it. questions? So that's assimilation. Now, as this molten rock is moving through the country rock, it's going to be changing in composition because it's going to be melting in, adding into the mixture the compositions of the country rocks. So that molten material, it can very well start as a massive magma at the beginning. But as it melts its way towards the surface and assimilates more and more felsic rock, then its composition will change as well. That's assimilation. As it's moving, it takes energy to melt cold rock. So as that process is occurring, the temperature of this thing is dropping. And you may reach a point where the temperature is just not enough to completely melt the country rock anymore. And you'll get these little blobs of, basically they're incompletely, incompletely melted country rock chunks. It loses texture, and it gets them started, but can't finish it. And when that's all completely solid, then you'll have like a big granite, but then it'll have like chunks of sandstone in it. Or it'll have chunks of marble in it, or it'll have chunks of some other rock in it. It ran out of heat. It couldn't melt those chunks completely into it. And of course, we scientists name everything. Those chunks are called xenoliths. Lith means stone. Those are going to be pieces of stone, pieces of country rock. Xeno means stranger, alien, foreigner. So stranger stones, meaning they're not from the original magma. They're foreigners that came in from the country. That's pretty much what that means. So now they're trapped in this igneous rock. Any questions? I have a feeling if I say one more thing, you're going to pop an aneurysm. I'm looking at it, your foreheads are flashing, brain full.
Yeah.
Brain full. That's hot in here. Get out of here.